Well, that's weird. Meeting is being recorded. Did you get that recording too, or not?
Yeah, I just got the message about that.
Okay. Has that ever happened before?
Not that
Usually
I
as a
know.
pop-up, but I don't think he's ever talked before.
Yeah. Oh man, all these sudden changes to software. What was it? Oh, the IPvo thing that I use suddenly came up with a bunch of additional steps this morning that I had to go through to be able to get it to display full screen mode. And I didn't tell it to do that. It did it on its own. I hope it's an improvement somehow. Let's see, are there any questions on the homework for this week? Anybody looked at the homework for this week?
Yeah. Question 1.
Okay.
As you pull it away,
Mm-hmm.
you mentioned that if you imagine the magnetic field being confined to a small circular area.
Yeah.
So as you pull it away, some parts of it will experience decreasing flux, other parts will experience an increasing flux.
Mm-hmm.
So the charges will move around. Do they move just straight across, or
They're not quite that tidy.
do they move in a more circular motion?
Yeah, it's kind of complicated, the motion of them, but the currents for the moving charges are always going to be at right angles to the magnetic field. And so
Okay.
That'll make a force that's perpendicular to both the current direction and the magnetic field direction, which will lie in the plane of the conductor that you're moving. That's one of the favorite demonstrations that I can do out in the class. I've got this little setup with it's a pair of neodymium magnets, or neodymium. I've heard it pronounced both ways, but they make very strong magnets. They're brittle, unfortunately. They chip very easily, or if you drop one, they just crack. But anyway, very strong magnets. And once I made the mistake of getting them right next to each other, stuck together, and I had to use a cutting knife to basically drive between them to finally get them separated. But anyway, in addition to that, I have this aluminum paddle with a little kind of pendulum mount for it. And if you don't have the magnet anywhere near the thing, you can swing that aluminum paddle and it'll just swing back and forth for the better part of a minute before it comes to rest. But when you put that magnet there, that it has to swing between the poles, 2 poles of this magnet, it'll stop like that. And it's just amazing, the magnetic braking. And aluminum is not magnetic. So it's just due to those induced charges flowing in the thing. And then there are some different shapes of the aluminum paddle. There's one that has slots cut into the thing that are still connected at the bottom, and that one will, complete like 3 swings before it comes to rest, whether the full, or where the full paddle would just stop almost instantly. And the one that has the slots cut into it, if you didn't have the magnet there, it would swing back and forth for the better part of a minute too. But then there's one where the slots cut into it aren't connected at the bottom, and so it's like the tines on a fork. And when you swing that one, it swings back and forth for quite a little while before it actually stops. It stops faster than it would if the magnet wasn't there. But the fact that the tines, or the individual pieces of that aluminum paddle, aren't connected at the bottom doesn't let the circuits or the currents that form connect at the bottom and go back in the opposite direction. And so you end up with much tinier currents in that case, and it swings longer. And kind of an amazing thing. Or you can do this thing where if the paddle is just hanging there at rest, you can move the magnet and it'll pull the paddle out with it. Although the force on the paddle is not in the same direction as a magnetic attraction would be. If it was a magnetic attraction, like if you stuck a paper clip in between the poles of that magnet, the paper clip would be pulled very strongly to either one pole of the magnet or the other, whichever one it happened to be closest to. Whereas the aluminum paddle is pulled perpendicular to the line between the poles. And so that's kind of a neat thing. And I think on that one video I showed you, didn't they drop a magnet down a pipe? Does that sound familiar? Maybe. I can't remember. Actually, I could call it up and we could look at it again. But out at school, I've got an aluminum pipe that there was one year, one of the people from LIGO came up here to do a bunch of demonstrations for kids, and they had to do with all sorts of stuff. But he had this aluminum pipe that it must have had close to a 1/4-inch wall on the thing, and he dropped a magnet down there, and there's no attraction between the magnet and the aluminum, but when you drop this magnet down the thing, and I'll do it with a neodymium or neodymium magnet, and it just looks like it's falling through thick syrup. It goes so slowly, and it takes, oh, I don't know, it's only about maybe a 1.5 meter long pipe or something like that. And it's not, or barely contacting the walls of the pipe. Once in a while you'll hear it hit if you don't hold the pipe steady. But it just takes close to 20 seconds to fall just that 1.5 meters there. And it's just amazing looking down the pipe while it's doing that it's moving so slowly. So fun stuff with, and it's induced electric fields, induced EMFs, and then the moving charges as a result of that. The magnetic field of the magnet exerts a force on the moving charges, but Newton's third law, those moving charges then exert a force backwards on the magnet itself. So that's what slows it down. Let me see if I can call up those things real quick. Where have I got them hidden? Oh, maybe drive E. I've got demo videos, that's it. Oops, that's not the right one. Oh, we already saw the motor, didn't we? Huh, maybe they don't have one. I thought they did. Yeah, I guess we don't have it. Okay. Tempted. I'm going out to school tomorrow for Taco Tuesday. And, oh, we're having a review session tomorrow, but I might be able to get that recorded and show you at the evening review session anyway. So, well, let's share the screen here and do some more things. So far we've been looking at changing magnetic flux through some kind of a loop or something that current can flow through. But turns out we have that effect happening whether there's a wire there or not. And let's save that for a second. Hopefully that's what we're looking at. So far, we've been using this expression that there's an induced EMF that is minus the d phi sub b dt. And the induced EMF is if you had some nice circular coil of wire or something like that, is as if there is an electric field in that wire, but there's no preferential spot for the electric field to exist in the wire. But if you did integrate an electric field around there in that circle, you'd get that induced EMF is from an electric field. And that electric field will exist in space, whether there is a wire for it to be in or not. So it's just going to exist in space. And this is actually a version of one of Maxwell's equations. They can be written a couple different ways, in terms of an integral or in terms of another derivative that would show up in here. And turns out that a changing magnetic field, you don't just have to deal with flux, you can deal with a changing magnetic field. It'll produce an electric field. And then there's symmetry. A changing electric field will produce a magnetic field. And it's that produces electromagnetic waves. In an electromagnetic wave, you can have an electric field that is existing in one direction in space. And this would be a kind of a plane, whoops, almost put the arrow on the wrong thing. So this could represent the electric field as a function of time. Coupled with that, since that electric field is changing in time, there would be a magnetic field, and the magnetic field is everywhere perpendicular to the electric field. And where the electric field is strongest, it turns out the magnetic field is strongest. There's a little bit of a phase difference between when the electric field is changing most rapidly and when the magnetic field is actually at its maximum strength. And so that ends up making the magnetic field and the electric field each have their maximum magnitudes at the same point in space. But this would be B in this direction and E in this direction. And you end up with something that the direction of travel of the wave, V, there's some kind of a proportionality constant in there, but it's got E cross B written into it. And so with E going in that direction and B in that direction, E cross B points in that direction. And so this would be the direction of travel of the wave. This would be E and that's B. And James Clerk Maxwell, or Clark Maxwell, I think they pronounced it Clerk, even though it's spelled, or Clark. Yeah, I'm not up on Scottish dialects very well, but anyway, he worked out the mathematics of this. Michael Faraday was the one who came up with intuitive statements for the way that you could describe these things, but he didn't have the mathematical background. And then Maxwell came along and tied these things all together. And we call the set of equations that describe all of this Maxwell's equations. And then Einstein comes along and shows that it's all a matter of perspective. So everything is relative, which is kind of neat. But anyway, today we're going to explore this idea and look at this electric field that's produced by this changing magnetic field. And the problems that I've got typed into here are from just for a solenoid. And so somewhere I'll have to track down that formula for the magnetic field at the center of a solenoid. But we have a long, thin solenoid with 900 turns per meter and a radius of 2.50 meters or centimeters. And the current in the solenoid is increasing at a uniform rate, 60 amps per second, which actually, if it's a high frequency, you could do this for brief periods of time and still not get all that large a current. Let's see, got to find the solenoid expression here. I think it's mu naught Ni, but I can't remember for sure off the top of my head. Yes, it is. Yep. Okay. We want to know the magnitude of the induced electric field at a point at a couple of different distances from the axis of the solenoid. And so solenoid has a radius of 2.50 centimeters, just about an inch. And we're interested in one that's half a centimeter from the axis of the solenoid and then 1 centimeter from the axis of the solenoid. So and 1.00 centimeters. And the expression we'll use here is this idea that if we integrate around one of these circuits, or circles, excuse me, and E dot dl, it will equal minus d flux of B dt. And we're just asked for the magnitude of the induced electric field in this direction. We're not that concerned with it, but if we had, say, the magnetic flux going into the page was decreasing, if there was a wire here, the current flow would be in a direction to try and maintain that decreasing flux. So if you had a wire here, if the current was going in this direction, then that would produce magnetic flux into the page, and it would work to counteract that decreasing magnetic flux. Here, we're not worried about the direction. We're just after the magnitude. And so we can forget about the minus sign. The E dot dl going around the circle, from the symmetry, you would expect the electric field to be in a circular loop, and the dl will always point in the same direction as the E, and so this thing can reduce to EDL, and the E should be constant if you're always the same distance away from the center, and so it can come out and you'll end up with E times the integral of dl just going around a circle. That's just going to be the circumference of the circle. And so E times 2 pi r, whatever the circle happens to be, is going to be equal to the flux of the magnetic field per unit time. And the flux of the magnetic field for a solenoid is reasonably constant near the center. It's just going to be mu naught Ni times the area of the circle that you happen to have. So that would equal d by dt of BA. And A is going to be pi r squared. So that's just the area of the circle. D by dt of B times pi times r squared. And the only thing that's changing in time is B. So we'll have E times 2 pi r is going to equal pi r squared dB dt. And the pi's go away. The electric field will end up being in magnitude. Let's see, we'll have a 1/2 here, and r under an r squared, 1/2 r dB dt. And things we can see here, the faster the magnetic field is changing, the more the electric field will be. It increases in strength as you go from the center out. So at the very center, there would be no electric field, and then it would reach a maximum value here. Outside of it, the total amount of magnetic flux isn't going to be changing as you go to even bigger values of R. So out there, you'd have a fixed value of R here and a growing value of R here. So the electric field will end up getting weaker as you move outside of the solenoid. But while we're inside the solenoid, we do have this going on. And they gave us the rate at which the magnetic or the current is changing, excuse me, which I didn't even work into here yet. Yeah, with B being mu naught Ni, the mu naught and the N can come outside of there, but I'll write it this way anyway. 1/2 R d by dt of mu naught Ni. And the only thing changing in that time derivative is the current. So, whoops, that's not what I want to write on. Slide one under here. Okay, that's the only thing that's changing, and the whole thing is changing as in response to that. So let's see, with mu naught being such a small number, this may not be terribly impressive, but we'll see. Oh, where did I put those things? Wow, 2 copies of that. There it is. Newtons per amp squared. So the induced electric field, 1/2 times 4 pi times 10 to the minus 7th Newtons per amp squared. Lowercase n is the number of turns per meter. This is 900. And unit-wise, it's turns per meter, but turns are just a placeholder word. I'm just going to call it meters to the minus 1. And then the R that we're talking about for part A, it'd be 0.500 times 10 or 5 times 10 to the minus 3 meters. So that takes care of the meters. Let's see. That was the R, that was the N, and di dt is 60.0 amps per second. Let's see. So meters are going to be gone. I would have newtons per amp second. Does that look like a an electric field to you? Check that. Newtons per amp second. Whoops, amp seconds. Oh, an amp second is a coulomb. Hey, that's newtons per coulomb. That's easy. That is an electric field. Okay, and the only thing that would change for part B is we'd be twice as far away. And so whatever answer we get for part A, we can just double it. We'd still be inside the solenoid for part B. So, and this is a different kind of electric field, by the way. 900. Whoops, it's small. I forgot what I was using this calculator for the other day. It must have been something to do with money. I'm showing only 2 significant figures. And okay, I get about 1.7 times 10 to the minus 4th, actually 1.70, we can keep, newtons per coulomb, which is a pretty weak electric field, so not super strong, but it's going to be twice as strong in part B, so for B it'll be 3.40 times 10 to the minus 4th newtons per coulomb. Still, that would be enough to, well, produce an electric field at least. But if you integrate all the way around the circle, you do get a potential difference as you're integrating around there. So that's something that happens. And this is a weird sort of electric field. It's not conservative. If you move a charge in a circle around this thing, it's going to have this electric field acting on it all the way around there, and the electric field will return it to its original point and will have done positive work on it. And so for this induced electric field, you cannot talk about an electric potential, because for a potential, something that can have a potential energy, if you take anything away from its initial point and return it to that point, the net work has to be 0. But you can have circular paths where you come back to the same initial point and the work is non-zero as you do that. And so for that reason, you won't be able to talk about an electric potential for an induced electric field from a changing magnetic field. And that's kind of weird. Okay, the rest of these problems are all very similar to this one. Solenoids every time, but they may change some of the rules on us. Long, thin solenoid, 400 turns per meter, which actually isn't all that many turns per meter. Radius 1.10 centimeters. A 6.50 microcoulomb charge moves in a circular path centered on the center of the solenoid, and that circular path is that far in radius and in a plane perpendicular to the axis of the solenoid. If the charge moves around the circular path in the direction of the induced electric field, how much work is done on the charge during one complete trip around the path? So this is looking at what we were just talking about. And then explain how it shows the electric field is non-conservative. Well, if the total work done and when you return to your initial point is non-zero, then it's a non-conservative force. How much work is done by the electric field during one complete trip around the path if the radius is 7 centimeters? Okay, well, let's kind of draw a better picture for this here. Okay, there it is. So here's the center of our solenoid. It's got a radius of 1.10, but we're going to be farther out than that. So that's the solenoid itself, and then this could represent the circular path that the electron's moving around. So okay, well, the magnetic flux in this case will equal mu naught Ni times the area that we've got there. So I'm just going to take a derivative of it already, but did I miss something? Or maybe we're supposed to leave this in terms, I better check the book, chapter 29, problem 31. I think I'm missing some information there because seems like I'd have to know something more to be able to calculate a changing field there. Long, thin solenoid. Okay, this must have been out of an earlier edition of the book. Oh, let's see. I didn't copy this in, but it says the current in the solenoid is increasing at a uniform rate, di dt. The induced electric field, nope, that's not it. They must have dropped this problem out of the later book, I think. Yeah, I don't see any way you can put numbers on this thing without knowing the rate of change of the current in this case. Well, let's make up a number for it. Let's see, in the previous problem, we used 60 amps per second. Let's just make it, yeah, that's a perfectly reasonable number. Then we can make this work. And the flux of B, since both these loops are outside of the solenoid, we can figure out the area of the solenoid and just always have that be the flux of B. It's going to be fairly constant. Let's see. Oh, let's calculate deflux of B dt instead, since I don't actually know the current. Let's see. Times pi times 1.10 times 10 to the minus 2 meters squared. Newton meters. Yeah, I think this will come out okay. Better make a note to myself to track down whatever edition of the book this thing came out of. It doesn't look like it's in the new one anymore. Yeah, they have a slightly modified version of this one, but not asking the same thing. Okay, well, it looks like we can calculate everything here. I actually have pi squared in there. Okay, I get about 1.15 times 10 to the minus fifth. Unit-wise, let's see. Let's see, meters squared times meter is going to be just a meter. Newton meters are joules. Joules per amp second. Or it's going to be Tesla meter squared per second, I think, as well. If I can track down that thing. Oh, magnetic flux. Tesla meter squared per second. Yeah. Amp is a coulomb per second. I think I lost a unit somewhere. Anybody see where it went? Oh, I'm not just having magnetic flux. That's magnetic flux per second. All right, that works.
Isn't
I think
the area meters squared? So you'd have an extra meters in there?
Well, yeah, this will give me meters squared, but that's meters to the minus 1. So a meter squared times a meter to the minus 1 is just a meter. So a Newton meter is a joule.
Oh, you have joules were in there. Okay, I thought that was.
Yeah, yep. And then I've got amp seconds on the bottom.
Well, that's joules per coulomb. That's a volt, isn't it?
Yes, that is. Okay, thank you. Yep. Yeah, which is what you'd expect for E.dl. All right. If the charge moves around the circular path in the direction of the induced electric field, We're talking about a 3.50 centimeter path. So the integral of E dot ds, or dl, excuse me, is going to end up being, again, E times 2 pi, I'll call this R1, I guess. Eventually, through the same argument I did on the last problem, that will equal this thing, 1.15 times 10 to the minus fifth volts. And oh, okay, we're talking about a charge this big. All right, the actual work that the electric field does is going to be the integral of Q E dot dl. Okay, this is the force on the charge. Force is QE. E dot dl, or QE dot dl, would be the work done. If I just pull the force out of there, I would have Q times the integral around the, or pull the charge out, E dot dl, and I would just have Q times 1.15 times 10 to the minus fifth volts, because the integral of E dot dl is equal to that thing. So Q delta V is the amount of work that's done on the charge, and well, steal this one. The charge was 6.50. It's not going to be much. Times 10 to the minus sixth coulombs times remember, a volt is a joule per coulomb. 1.15 times 10 to the minus fifth joules per coulomb. So we'll just end up with work in joules and a small amount. Let's see. Okay, but if it's a little tiny charge, although with a charge this great, it's not going to be that tiny. This is going to have a whole bunch of electrons worth on it, or protons worth on it, but I get 7.45 times 10 to the minus 11th joules that is the amount of work that's done on this charge. Let's see. How does that confirm that the electric field is non-conservative? Well, we started at some point. We come back to that very same point, and the net work done is non-zero. So for a conservative force, the net work would be zero, because if you just go away from here and come back, the electric, or the work generally is going to be zero for a conservative force. But if you come back to the same point and it's non-zero, it's not a conservative force. So you could just keep going around in circles here, keep adding to the amount of work that's done on the charge, and it's going to keep increasing in kinetic energy if it goes around something like that. But you're having to pump energy into this thing to have a changing magnetic field. So it comes from somewhere anyway. And if we went around a path with twice the radius, the amount of magnetic flux is the same, and the time rate of change of the magnetic flux within the area is the same. But let's see. Yeah, the electric field will actually drop off like 1 over the distance, but the circumference increases proportionately to the distance. So you end up having the same amount of work done. Because distance around the circle increases with the radius, but the electric field strength decreases with the radius. So won't be quite so interesting. Okay, let's see. This is just another very similar problem. Oh, this time we're supposed to calculate di dt. So long thin solenoid again. B is equal to mu naught Ni. So that the current in the solenoid increasing at this uniform rate, the induced electric field at a point near the center of the solenoid and 3.50 centimeters from its axis is 8 times 10 to the minus 6 volts per meter. So this integral of E dot dl, which we can simplify to E times 2 pi r, which will equal in magnitude d phi sub b dt. We can use this, and for the flux of B, let's see, that's the radius of the solenoid. This is the radius of the path, which I'll call R1. I'll call this thing R sub S. So that's R1. The magnetic flux is going to be contained inside the solenoid pretty much. And that will equal B times A, which is going to equal B times pi times the radius of the solenoid squared. Whoops, that was supposed to be a B. So we have that. And the magnetic field is going to be mu naught Ni, so we'll have mu naught lowercase n I times pi times the radius of the solenoid squared. All kinds of things strung together on this, and the time rate of change well, the only thing in this whole expression that's changing is the current. And so I would have mu naught times n times pi times the radius of the solenoid squared times di dt. And this will equal E times 2 pi R1. So this time I don't have the same R's here and here as we did on a previous problem here. But we're supposed to calculate di dt when the electric field, we know the electric field strength in this case. So we know everything here, and we know everything here. The only thing we don't know is di dt. So divided by all this stuff, mu naught n pi r sub s squared, and the pi is at least, oh, that makes it much simpler. Okay, 2 times R1, that was the 3.50 times 10 to the minus 2. Meters. And then E is 8.00 times 10 to the minus 6th. Volts per meter. Or joules per coulomb meter. Let's see, and on the bottom, 4 pi times 10 to the minus 7th. Newtons per amp squared times N, which is 400 meters to the minus 1 times, 1.10 times 10 to the minus 2 meters squared. Man, if only I developed the habit of starting to write from the left side instead of partway down the page. Too late now. This might have been easier to do stepwise, calculation-wise, but we'll see if this works. Let's see. A meter times a volt per meter, that's just going to be volts on top. And I better do that somewhere. A volt on top, and on the bottom, I'll have a Newton per amp squared times a meter to the minus 1 times a meter squared. Okay, so meter squared times meter, that's going to be a joule per amp squared. A volt is a joule per coulomb divided by a joule per amp squared. I'm missing a second here somewhere, I think. Oh, I know why. The joules go away. I'll have amp squared over coulombs, but an amp is a coulomb per second. And I still have an amp on the top. Amps per second. That makes sense for di dt. Okay. So I don't know what the point is of plugging all the numbers in, but we would find out how rapidly the current happens to be changing anyway. So I better clear everything out of here. Eight times 10 to the minus 6. Well, I hope I didn't foul this up. I get about 9.21 amps per second. So looks like we had 3 sig figs on everything they gave us, except the 400 turns per meter, except those you can actually count. And so you might have exactly 400 turns per meter. Okay, well, that kind of did that to death. But the main idea here is if you have a magnetic field that's going in some direction, and that magnetic field is either increasing or decreasing in space, and you've got cylindrical symmetry, there will be an induced electric field that forms concentric rings around that thing. And that's just bizarre. But the whole thing works out to be that the integral of E dot ds around this circle is going to be, if you're concerned about the sign of the electric field, the safest way to do it is to use Lenz's law and imagine that there's a wire going around here, and then look at whether that magnetic field into the page is increasing or decreasing, or if a magnetic field out of the page is increasing or decreasing. But it'll be described by that. And if you have cylindrical symmetry, then the electric field will be the same strength at any particular distance from the center of that. And so, whoops, that's an L, not an S, although it doesn't matter. anyway, E and DL will point in the same direction, which means the dot product is just EDL, and you can pull E out, and DL is just the circumference of the circle. And you can find the electric field if you know this. And if you know the electric field, then you can use that to find di dt. So that's the big idea. Changing magnetic field produces an electric field, and vice versa. Changing electric field will produce a changing magnetic field, although we did not investigate a changing electric field. Okay, tomorrow we'll have a review day for a test on Wednesday, and I'll post some stuff later today. In fact, I was just looking at the sheet for it concerning that, the review material. And let's see. Well, I'll try to put out a doodle poll and see when the best time to have a review would be tomorrow. But it ought to work. And we can talk about the homework assignment too during that stretch. So where am I? Stop share. Anyway, we can have a review session tomorrow, see how that works out. I think nearly everybody's here. It looks like this time might work for a review session, but oh, who am I missing? Riley, Grayson, Nolan, Philip. Oh, Noah is not here, but I'll find out when he could do a review session as well. We might have possibly a second review session tomorrow, although I am also giving a Physics 114 test at 2 different hours tomorrow, although one of them is going to be at 10:30. So we'll see how that stuff works out anyway. So otherwise, be thinking about questions for tomorrow and take a look at last year's test when I get that posted, and also the list of review topics, and try to generate some questions for yourselves out of those. And we'll go on from there.